Okay, so given these points, we chose to approximate the straight line that we think represents what's actually going on by running a line through the first and last points. And we see that worked out really well for some of the points, but the line didn't come all that close to some of the others. We found the equation of the line to be y equals 0.52x plus 0.48. This is our attempt at doing a line that does a good job of fitting these points. Let's assess how well we did. Okay, first place, we can make a table, and I've estimated the coordinates of these 1, 2, 3, 4, 5, 6, 7 points, 1, 1, 2, 1.52, etc. Then I've listed the x and y values. The x values I've estimated to be 1, 2, 2.3, etc. The y values would be these. Now you can look at this graph and you can make your own estimates of what these coordinates ought to be. Having made our estimates of the coordinates, what we're going to do is we're going to do y predicted. We're going to predict the y values based on the equation and the x values. So for example, when x equals 1, we plug 1 in here. Okay. For example, x equals 1 implies y equals 0.52, not 50, times 1 plus 0.48, which is equal to 1. So that when x equals 1, y equals 1. Now that's exactly what we should have expected, because the 0.11 was one of the 2 points we chose as the basis for the equation of our straight line. If we had gotten something besides 1 when we did this, that would not have agreed with the idea that the graph that the line goes through the 0.11. Now, if x equals 2, I chose 2 for this point, so x equals 2 would imply that y equals 0.52 times 2 plus 0.48, and 2 times 0.52 is 1.04. You add 0.48, you get 1.52. And that's exactly what the y value came out to be. And that's not surprising, because it appears that this point and this point and this point lie on the same straight line, at least the way I modified the graph. Okay, so our predicted y value is 1.52. That agrees with the y value that we estimated from the graph. Now x equals 3. Okay, well, it's going to be 0.52 times 3, which is 1.56. We add 0.48, and we get 2.04, as you can easily verify. Now, I kind of messed up there. I did the x equals 3 point. Here x equals 1, here x equals 2, here x equals 3, and I skipped this point here. The x equals 3 point appears to lie on the graph, so that our prediction again agrees with our value. I don't have these coordinates over here lined up very well with my table, and that caused me to do something other than what I intended to do, but that's okay. X equals 3 gives us 2.04, and that gives us good agreement. Now x equals, let's come back to this point, which I estimated to have an x coordinate of 2.3. That implies that y equals, well, you can plug 2.3 into this equation, and you can verify, and if I'm wrong, you can correct me. You can verify, though, that I believe this is correct, that this point is y equals 1.68. Now for this point, unlike these three, which all appear to lie on the straight line, for this point, which doesn't lie in the straight line, our prediction is 1.68, and that does not agree with the y value on our graph, which I estimated to be 1. Similarly, the x equals 4 point, which would be this one, lies below the graph, so that the value estimated, the point on the line corresponding to x equals 4, is going to be higher than the point on our actual graph, than our actual data point. So that at x equals 4, we predict 2.56, which is perfectly reasonable. If x equals 4, we come up to the graph and over, and we see that we're a little over 2.5. But our data point is only down here at 1.8, somewhat below 2. Okay, well, we have these points, and we have good agreement on this point, and this point, and this point, and this point, this point. It also I believe on 4.7, there are 5 points that appear to lie on the line, so we have real good agreement here on these 5 points. But these 3 points that lie off the line are significantly different. We have a significantly different y coordinate than predicted by our equation. And now what we want to do is we want to ask ourselves, well, by how much do these points deviate from the prediction? How much does the prediction deviate from the actual data, or how much does the data deviate from the prediction? So I would suggest to you that you stop for a minute and calculate your deviations. Now the deviations where you have complete agreement are all 0. Now we have a little bit of a discrepancy here. We'll give that a 0.2. But for these circled points, the deviation is either 0 or very close to 0, and that should be 0.02, not 0.2. Now we have 3 points here where there are significant deviations. You ought to go ahead and calculate those just for focus and so forth. Well, hopefully you've done that. I went ahead and did it. The deviations are 0.68, 0.76, and 1.29, unless I've made an error. And if we add these up, we get what? 0.68 and 0.76 is 1.44, 1.46. So that's going to be 2.75, I believe. And I'm going to label that as the sum of the deviations is 2.75. Now, let me make sure we understand this summation symbol. This symbol simply says, I call it the atom up sign. Okay, it's a Greek capital sigma. It means sum up the deviations. If we sum up the deviations, unless I made an error in the arithmetic, which is perfectly possible, we have 2.75. Check my arithmetic and make sure. That's the total by which these points deviate from the straight line. So one of our deviations here, the deviation 0.68, okay, that deviation is 0.68. This deviation appears to be, 0.76, and this deviation appears to be somewhat greater at 1.29. If we add up those deviations, we get 2.75. And that is one measure of how well we did when we approximated our data by the straight line through the first and the last points. Now there's a better measure of the discrepancy. Well, an improvement of the measures, not just the sum of the deviations, but it's the average deviation. And that's going to be the sum of our deviations. In other words, we add these up, and then we divide. There are 1, 2, 3, 4, 5, 6, 7, 8 points on this graph. So the average deviation is 2.75 over 7, which is approximately equal to 0.4. It's actually 0.39 and about 393. But it's very close to 0.4. Okay, actually rounds off to 0.39, so I could have written that as 0.39. That's a pretty good measure of how we did when we fit our straight line. But there's an even better measure, and you can probably guess what it might be. Okay, you might want to pause and think about what it might be. Well, hopefully you've paused and thought about it a little bit. What it is, in this case, is the standard deviation of these points, the average of the squared deviations. That is for reasons that we can't go into unless we do the calculus of the best fit line. There are very good reasons why we think that the standard deviation of these points relative to the data points, or the standard deviation of the data points relative to the prediction, is our best measure of how well we did with our prediction. So we're going to calculate a standard deviation. So we take, what do we do to calculate the standard deviation? Well, we average the squared deviations and then take the square root. It's very familiar. Now I'm going to go ahead and write a few things down here off camera, but you should go ahead and do this deviation squared, and actually, if you can, go ahead and do what you think would be the standard deviation. And I'm going to move this board over a little bit. Okay, I've squared the deviations. See if this agrees with what you got. What would I do next? Well, it certainly makes sense to add up our squared deviations. What would we do next? Well, it appears that the average of our squared deviation is 3.67 over 7, which is 0.52. Or, since n is less than 30, we have fewer than 30 points, maybe we want to do 3.67 over 1 less, 6, and we get 0.61. Kind of a significant difference, but this gives us another measure of how well we fit the data points with our function, choosing the first and last data points in this case. Now it turns out that this is not a standard deviation, and we're just going to talk about the average of the squared deviations to contrast with the calculation of standard deviations. So in this case, we're just going to take the average of the squared deviations and use that as a measure of how good our mathematical model is. Our mathematical model being our straight line. Now, the next question that we want to pose is, can we improve on this? Can we improve on this average squared deviation of 0.52? And my equal sign there kind of almost looks like a negative sign. Let's go ahead and make sure we see that as an equal sign. I kind of obliterated part of the equal sign with my circle. Okay, so the next question again is, can we do better? Can we do better by putting the line someplace else?